and welcome to today's lesson. Today we're going to look at something called the hyperbola, and I'm starting off with a very simple example, and I'm basically going to show you all the bits and pieces and ingredients of this example, and then we're going to look at a few other things as well. So let's start off. Now you'll notice a couple things about the equation here. First of all, I'm working in standard form, which is my favorite for graphing. But you'll notice you've got basically, there's going to be an x squared term and a little bit of a number here. Then there's a y squared with a bit of a number. And there's a minus sign, okay? So these are different. This one's positive, the x squared, and this one's negative, and then equals 1. Now that's very different from circles and ellipses where we had x squareds and y squareds, but they both had the same sign. Most cases they were both positive. So very different, one's positive, one's negative. So let me just show you how we graph a hyperbola. Well, we start off with the same kind of logic that we used with circles and ellipses. First of all, I made this one fairly simple in that there is no shifting. Okay? If there was shifting, I would have dealt with that right away. You'll see that in later examples. So what I'm going to do is I'm going to say, yes, the center is 0, 0. And on the x-axis, I want to go 3 to the right and 3 to the left. So let's mark that down. Now, I'm going to mark that spot with a little bit of an X. And you'll see why I don't just put a solid dot there in a moment. And 3 to the left. Okay, marked with an X. On the y-axis, I want to go up 2 and down 2. So up 2. Marked with an X, and down 2. Now what we have created here with hyperbolas, these are basically the guidelines of a little box. So what you do is you kind of build a little rectangle based on these dimensions. So you can see I'm going through those points, and I'm building this little guide box here. Okay, now you might say, well, what's the point of that? Well, I'm now going to draw through the center of my hyperbola and through each corner diagonal lines. And these diagonal lines have a special name. They're called asymptotes. And they're very important for helping us draw the appropriate shaped hyperbola. Now this is where a ruler is rather handy. And I don't have one, so I'm going to try and draw the straightest line that I can through these. There's my one diagonal line, and here comes the other one. Okay, so these are called the asymptotes, and now what we're going to do is try and fit in the hyperbola. Now, we have a choice with hyperbolas, and if you think back to our original discussion about what a hyperbola is, you might remember that there are kind of two shapes to it. They look almost like parabolas, they're not quite, and there's two parts. So you either expect it to go like this, or you expect it to go kind of like this. Okay? So what we have to do is decide, do we want these 2 points to be what we'll call the vertices of the hyperbola and fit it in here, or do we want to draw it vertical, making these 2 points our vertices and fit it in like this? Well, here's how I make my decision. I simply use a test point. I take a look at this point here and say, well, this is the point 3, 0. If it works, if the original equation works with these coordinates, then this is an actual point on the graph telling me that there must be a piece of graph over in this section. So I'm going to test it out. So I'm going to plug it in here. I'm going to put in 3 for the x. And let's see where I can fit that in. See if I can cram it in over here. So I'm going to put in the 3, minus, and then put in the 0 for the y. And see whether or not it equals 1. Well, what you'll see is you get 1 squared, which is 1, minus 0 squared, which is 0. And that is a true statement. So it works. Well, if it works for this point, it means it's a point on the graph. And that means that we've got one section of our hyperbola is on this right side. So I'm going to fit it in And this is where the asymptotes are very important. You can see they're kind of guidelines to show you how to make the graph shape. Whether to make it wider or narrower, that's determined by the asymptotes. What you try and do is snuggle your graph up towards these lines. Keep in mind that the graph actually never does touch these lines. It just approaches those lines, hence the name asymptote. Well, that's the right side of the hyperbola, and that means we have a left side as well. The interested student could, of course, test out this point, -3, 0. You would find that it also works. So there's the graph of our hyperbola. Now I'm going to tell you a little bit of notation here, a little bit of vocabulary. We've identified that the center is at 0, 0. And we've identified the vertices. We said that one was at 3, 0, and the other one is at -3, 0. But there's also some other terms. The distance or length from one vertex to the other vertex, okay, this distance along here, that is called the transverse axis. I'm just going to write that down for you. Transverse axis. And in this example, that would be 3 and 3, so a length of 6. The other axis actually doesn't go from a vertex to a vertex, but it is an important dimension, and that is called the conjugate axis. And in this example, it was a length of 2 and 2, which is 4. There's one other piece of information that's often requested with hyperbolas, and that is, what are the slopes of these very important guidelines, or asymptotes? Well, if you think about it, it's very simple if you use the rise and run approach. If we use a little triangle like here, we know that we went up 2, and we went over 3. So this would be a rise of 2 and a run of 3, so 2 over 3. So the slopes, and I'll just put them up here. And I want to show you the word asymptote because it's rather a lengthy one to spell. So, slopes of the asymptotes. Asymptotes. Okay, so you know exactly how it looks. Well, we have one is +2 over +3, and this guy over here is also 2 over 3, but it's negative. So we combine that and just say it's plus or minus 2/3. And that's our first example. That's a nice little hyperbola, all drawn out. Well, half erased now. Okay, let me move on to a little bit more complicated example because it involves some shifts. So, all right, so in this example we're going to take x minus 1 over 2 all squared minus y plus 4 over 5 all squared. And this time we're going to throw in a little twist. We're going to make it equal to -1. And I can show you exactly what effect that's going to have. Now just so you're aware, I'm going to erase it here, but just so you're aware, if you sometimes see -1 written on the right, sometimes you see +1, and sometimes they rearrange the same equation to kind of a little tricky form. If you multiplied everything through by -1, you would be turning the right side into +1. This would become negative. This expression here would become negative, and it would be often written like this. Okay, and then this minus y stuff becomes positive, and so we write it out front. So not to be spooked if you see something like this, okay, where they started with the y squared minus the x squared stuff. It's in fact the same as the original equation. So just be aware of that. This is a very common way to write it. All right, back to graphing. So let's get our picture here. This time we have some shifting to deal with. Well, I'm going to go 1 to the right. We want to shift over on the x-axis to positive 1. And I'm going to put in a little guideline. And on the y-axis, we want to shift down to negative 4. 1, 2, 3, 4. And again, putting in a little dotted guideline. So the center of this hyperbola is now at 1, negative 4. Maybe I'll just make a little note of these things as we go through it. So 1, negative 4. Okay? Well, now that I've done that, I ignore the shifting. I ignore the minus 1 and the 4. And what I'm going to do is basically graph the hyperbola, treating this as the center point, and forget about shifting. So it's kind of makes it a little bit easier, I think, if you do that. So what do we have going on here? Well, let me just rewrite the way the equation would look without the shifting. You're going to have x over 2 squared minus y over 5 squared equals negative 1. Okay, so that's what we're going to graph at this new location. On the x-axis, I want to go 2 to the right and 2 to the left. So 2 to the left and 2 to the right. Okay. And on the y-axis, I want to go up 5 and down 5. So 1, 2, 3, 4, 5. And down 1, 2, 3, 4, 5. So that gives us the dimensions for our little framework. So we're just going to put that into the picture now. Lots of dotted lines on these things. Okay, very, very nice and neat there. Okay, what I want to do now is complete the asymptotes here. Remember, they're the diagonals of this little box and they go through the center. Try and draw it as straight as I can. Okay. All right. And now the big question is, do we want our hyperbola to go like this on the left and right side, or do we want it on the top and bottom? And here's an easy way to test. We just take a point. Like, what about this guy over here? Well, remember, I'm ignoring the shifts, and I'm pretending that the center here is 0, 0, and I'm using the simpler to work with equation. And so I would give this guy the coordinates 2, 0. And I'm going to try those out in this equation, the one without the shifts, and see if it works. So if I put in 2, I'm going to have 2 over 2 squared minus 0 over 5 squared, and that's supposed to equal negative 1. Well, it won't take you very long to see. You're going to get 1 squared, which is 1, minus 0 squared, which is 0. Well, that does not equal negative 1. Okay? In other words, this point does not work. What does that tell you? Well, then this isn't the vertex. So it must mean we're dealing with vertical stuff here. So I'm going to go with this guy up here and this guy down here. There's our hyperbola. And if you wanted to, you could test out this point here. Again, if you use the simpler equation without the shifts, you'd want to plug in the point 0, 5. And just plug them into here, and you would find that it does give you a true equation, meaning that that was the correct way to fill in the hyperbola. Okay, that being done, let's identify some of the other bits and pieces, like the vertices. Now be careful. I used 2, 0 here and pretended that that was 0, 0. But in fact, these are not the actual coordinates of this point. And neither is the actual coordinates of this point. It's certainly not 0, 5. Okay, that's only when I use the simpler equation. I'm going to erase this because it's actually not the true coordinates. So when I'm looking at the vertices, I have to go back and say, well, I'm not dealing with this hyperbola. I'm dealing with this one, which had shifts. So we went 1 to the right, and then I went up 5 from this point here. Well, if I go up 5, that's 1, 2, 3, 4, and here's 5. So that's actually the coordinates 1, 1. Okay? And similarly, from the center point, we're at 1, and then we went down 5 more. We're at a y value here of -4, and so if you drop down 5 more, you're at -9. Okay? So just be careful that you don't get fooled. This is not 0, 0. Okay? The center is in fact at 1, -4. And we should identify the transverse axis. Now, here's a little way, and it's kind of silly, but it works, a way to remember which one's which, because you got your transverse and your conjugate axes. So which one's which? Well, I think of the vertices here as little cities, okay, like on a map. And basically, if you're transiting, okay, from one city to the other, then that steers me towards transverse axis. Okay? Transiting from one city to the other, transverse axis. So I know it's from vertex to vertex. And then the other one, well, it's the other one. So transverse axis, that was 5 and 5, so that's 10. And then this guy over here is 2 and 2, so a grand total of 4. And then we want to identify slopes of the asymptotes. They're going to be plus or minus. And all you have to do is think of one of these little triangles here. Well, it's up 5 over 2. So we're talking plus or minus 5 halves. And there's that example, all wrapped up. A beautiful little hyperbola. I do find them quite lovely. Okay, moving right along to the next example. Now the next one is not going to be presented to you in standard form. So what are you going to do if you've got a general form equation, something like this? So x squared minus y squared minus 4x minus 4y minus 9 equals 0. What are we going to do with that? Well, we have to do what we did with the circles and ellipses, and that is complete the squares and group things together and get it basically to standard form. So here's what we have to do. Okay, let's go with x squared minus 4x. Leave a little space. Then we're going to have the minus. Now, this is where you have to factor it out. Okay, whether you like it or not, we bring the negative sign, factor it out, and when we group in the minus 4y, we've already got the minus sign on the outside, so this becomes plus 4y. Leave a little space, and then the extra number I add to the other side. So now I'm going to complete the squares. Half of negative 4 is negative 2, squared is 4, and I compensate by adding the same thing to the right side. Over here I need half of 4 is 2, squared is 4, but be careful, that's an actual negative 4 that you brought into the picture. So when I compensate, I'm putting a negative 4 in on the right side. Well, here's what it now looks like when I factor it all together. I've got x minus 2 squared minus y plus 2 squared equals 9. Divide everything through by that 9 so that we have it equal to 1. And here's what my final standard form would look like. I have x minus 2 over 3 squared minus y plus 2 over 3 squared equals 1. So I now have it in lovely standard form, and I'm ready to go ahead and graph it. So what I'm going to do is make a little space over top and get to graphing. Alright, let's see what we can do with this. Okay. So, let's get the shifting out of the way. On the x-axis, I want to go to positive 2. And I draw a little guideline. On the y-axis, I want to go to negative 2. Draw a little guideline. Okay, so there's my center. Make a little note to self here. Some questions will ask for the centers, others won't. But anyway, it's easy to identify. It's 2, negative 2. Okay. Next thing I notice is that on the x-axis, I want to go 3 to the right and 3 to the left. And similarly, on the y-axis, up 3 and down 3. So 1, 2, 3, 1, 2, 3, up 1, 2, 3, and down 1, 2, 3. And there's a name for this kind of a hyperbola. When you get a square, when your little framework here turns out to be a square, it's kind of a strange name. It's called a rectangular hyperbola. Now you might say, but that's a square. Why is it called a rectangular hyperbola? And it has to do with the following. It's called rectangular because these diagonals, albeit not well drawn, are at right angles to each other. And that's actually what a rectangle is. It's a shape that has right angles. So in this case, that's why it's called a rectangular hyperbola, because the asymptotes are perpendicular or right angled to each other. We recognize that actually in the equation itself. Whenever these two numbers are the same, then you know you're dealing with a rectangular hyperbola. So now the only question is, where are the vertices? Where are the vertices? Well, let's try a little test point. Now this one here, if again I treat this as 0, 0, this would be the point 3, 0. And so I would test it out in the simpler version of this, the one ignoring the shift. I would plug in 3 and 0. And you'll notice I'm ignoring the shifts. All I want to know is, does the point that's 3 units to the right on this x-axis, does it work? And you can see 1 minus 0. Yes, it does. So that is a vertex. Shoop. 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 And zoop. Okay. Special sound effects thrown in for that one. All right, let's wrap it up. There's the picture of our rectangular hyperbola. Quite lovely. And where are the vertices? By now, you're probably able to shout them out. However, I'll still figure it out myself here. And then there's 2 to the right, and then 3 more, so that's a 5. And we were 2 to the right, and then we went back 3, so that would be negative 1. And they both have a y value of negative 2. So there's the vertices, and now we would just want to figure out the slopes of the asymptotes. And I'm going to show you an extra little twist in this one, which is kind of neat. I'm going to need some room here. Suppose they said they wanted more. Suppose they wanted the equations of the asymptotes. So here's what you have to do. You start off by saying, without the shifting, what kind of equations would I have for these two lines? Well, lines look like this. They're y equals the slope times x plus the y-intercept. But of course, if I pretend that this is 0, 0, there is no y-intercept. So I start off with this sort of template form, and I say, well, the slopes of these asymptotes are, in this example, they're plus or minus 1. The reason is 3 over 3. So here's what I have as my kind of template equations. And then we bring in the shifting. So it's kind of a neat little idea. Now I've erased the equation, but we look at the graph. We wanted to shift it 2 to the right, which means for the x, we wanted to see x minus 2. So what I did was I just included the shift now in with x. And with the y, what kind of a shift did we want? We wanted to bring it down 2, so we need y plus 2. Well, believe it or not, these are the equations of the asymptotes. It's kind of a neat little way to do it. First, you find the slopes, so you include those slopes, and then you bring in the shifts, if there are some. And if you simplify this, and I guess I could do that over here. If you simplify these expressions now, you'll find you get 2 uniquely individual equations for these 2 different asymptotic lines. So, for example, if I do the plus one, so I have y plus 2 equals positive x minus 2. Well, how would I finish this? I just subtract 2. So here's one of my equations. Okay? Now let's see which one that is. That would be a slope of positive 1 and it should have a y-intercept of -4. Yeah, that looks about right. This has a slope of +1 here, and it looks like it's crossing at -4. Now the other one would be y plus 2 equals -x minus 2. Okay, so let's clean that up a bit. We'll subtract 2 over, so we're going to have -x, and then a double negative, so that's +2. Oh, and then we're subtracting 2 over, so we would expect the other asymptote to simply be y equals -x. Well, look at that. There it is, y equals -x. So that's kind of a neat little way to find the actual equations of the asymptotes. All right, we're on to our last example. This one's, well, you know, they always get a little trickier as we go through, so this is probably the trickiest one to date. Here's what we have. In lovely general form. I say that sarcastically because I don't find anything lovely really in general form, but, whoops, I wrote this wrong. You get talking, you know, you get monologuing like that, and you start writing it out wrong. Anyway, it doesn't matter, I fixed it. So, okay. And then a +76 equals 0. So, okay, so a really nice, big, messy one to work with, but not so bad. So we know what we're doing. Okay, let's factor out the 9 and group all the x stuff together. We got 9, and that would mean we've got the x squared there. Here comes positive 54x, which means I want plus 6x, and I'll leave a little space to complete the square. Then, oh, I just got to factor out the minus that's in front of the y squared. So this is positive 2y, but the negative's already out, so negative 2y. And over on this side, minus 76. Okay, let's complete the square. Half of 6 is 3, squared is 9. But I actually brought in positive 81. So I got to do that over here, plus 81. Here I have half of 2 is 1, squared is 1. But I actually brought in -1. So I've got to bring in -1 over there. So let's see what we have now. We got 9, then we got x plus 3 squared minus y minus 1 squared equals, and what do we have here? 81 take away 1, so that's 80. Take away 76 is 4. And we want to divide everything now by 4 so that we have a 1 on the right. Okay, well, this is getting good except for one problem. It doesn't cancel very nice. So I'm going to use the same trick that I used before. And that is, I'm going to take this 9, I'm going to get rid of it, and put it under the 4. It's a neat little trick, so you get rid of these little extra numbers hanging around the numerator. So now here's what our final equation looks like. We have the x plus 3, and underneath it, the very, very nice 2/3. Okay, so you might say, oh, 2/3, but that's okay. Fractions are our friends sometimes. Okay, and then over here we have y minus 1 over 2 all squared equals 1. So I'm ready to draw the picture of this thing. All right. Let's get rid of this now. Make a little room and draw ourselves a picture. And I don't think I'll bother. Well, maybe I should. We'll see. See how motivated we are. Okay. We want to shift to -3 on the x's. 1, 2, 3. On the y's, we want to shift to +1. Okay. On the x's, we're only going 2/3 to the right and 2/3 to the left. So it's kind of like there and there. Just sort of eyeballing that. And on the y-axis, we want to go up 2 and down 2. So up from the center, we want to go up 1, 2, and down 1, 2. So here comes the little box. And it really is a little box. Okay. Draw the asymptotes. Alright, now we're set. Now after a while you'll gain a certain amount of comfort and speed that when you go to test out which way your hyperbola should go, you probably won't have to write everything out. I mean, right now I'm looking at this and I'm thinking, okay, ignore the 3, ignore the -1. If this was 2/3, and so what I'm doing is testing my favorite point here, if that was 2/3 over 2/3, that would be a 1, and 1 squared does end up equaling a +1. Okay, and of course this would have become just 0. So it doesn't take you very long to see you've got quite a wide hyperbola. There it is. Absolutely lovely. Okay, let's rattle off some of the important information like the vertices. Okay, so we've gone, the center here was 1, 2, 3 to the left and up 1. So I know the y value for my vertices, that's 1. Now from this -3, I've gone 2/3 to the right. So I'm going to be at -2 and 1/3. Now, I like mixed numbers, and a lot of people don't. These days you get more and more decimals seem to be all the rage, I guess. But I like just working with mixed numbers. I think in some sense it's easier. And from -3, if you go 2/3 to the left, well then you want to be at -3 and 2/3. Okay, so there we have our vertices. And if we wanted to do the transverse axis, that means we're just going 2/3 and 2/3. Gives us a grand total of 4/3. Conjugate axis, a little bit easier. We are going up 2 and down 2, so that's 4 in total. And I'm just going to show you the slopes of the asymptotes. And they're a little strange because you've got a fraction within a fraction, but it's not too bad. Think of your little slope triangle. We have a rise of 2 and a run of 2/3. And you might go, yikes, that looks awful. Yes, you have a fraction within a fraction, but here's a quick way to clean it up. Just times the top and bottom by 3, because then you'd have plus or minus 6 over, and the 3's cancel, over 2. So you have plus or minus 3. So not too bad at all. And I must say with that, I am utterly and completely drained of energy. So I will catch you later.